Well, welcome everybody to tonight's meeting. Actually, I need to say, I sincerely hope that everybody is doing along okay with what seems to be a continuing, really not very normal time. However, there does seem to be some sort of wind of optimism gathering for 2021, so fingers crossed for that. There's only a couple of things I wanted to mention this evening, and the first is, of course, our next meeting, which is our Christmas quiz on the 11th of December. And as always, it will be designed and compiled by Jeanette Noble, and of course presented in some style by Graham Young. I mean, a pandemic can't possibly interfere with our Christmas quiz. So I recommend sharpening pencils and actually just pouring a glass of something pretty strong. But maybe Jeanette will be kind to us this year and make it a bit easier. At least it's less embarrassing scoring it up at home. And the second item is our members' night, which is the first meeting in January, on the 15th of January. It's just a lovely meeting where people can present absolutely anything, pictures taken, places visited, thoughts had, whatever. And if you would like to present anything, just get in touch with David Patterson or with Graham McAteer, and they will help you with any IT issues, because we'll still be Zooming. But tonight we have something much closer to look forward to than 2021, because we have our guest speaker here and now. And I am delighted to be able to introduce Stephanie Campbell, who is from the University of St Andrews. And Stephanie tells me she's currently in second year postgraduate and has finished her undergraduate and her master's at the University of Edinburgh. So tonight, Stephanie is going to speak to us about dark matter, crucial for formation of cosmic web, galaxy formation, so fairly big, important things, and telling us something about what seems to be an undoubtedly tricky business of how you can learn more about a substance which is definitely dark. So I'll hand back over to Stephanie and David, and as always, any questions, send them in on the chat facility. So back to David and Stephanie with thanks.
David, you're muted.
Can't hear you, Dave. We can hear Stephanie, so just go.
Thank you, David, for what I'm sure was a great introduction. I will share my screen and I'll go ahead with my talk. So thanks, Jim, for a wonderful introduction. I'm Stephanie Campbell. I'm a PhD student at the University of St Andrews, and I'm very pleased to be able to join you tonight and speak a bit about what it is that I do. Joining you virtually, it's a shame that I can't join you in person, but obviously the current situation warrants that I keep my distance. So I hope that everyone, as June said, I hope that everyone and their loved ones are safe, especially as we head into sort of darker winter months. And perhaps the topic I'm speaking about tonight is quite appropriate as we head into these darker months, because I'm going to speak a little bit about dark matter in galaxies, what we know about it, how we know about it, what we still need to find out about it, and how it is that we actually go about finding out about it. So to begin with, I'm going to run through sort of a shopping list of what is actually contained within a galaxy. So here you can see a lovely picture from the Hubble Space Telescope of Andromeda, sort of our nearest large galaxy neighbor. And Andromeda, the first sort of thing that stands out of you in a picture of any galaxy is the galaxy contains stars. So Andromeda contains about 1 trillion stars. Our Milky Way contains hundreds of billions of stars. And you get sort of smaller galaxies that contain thousands, but there's lots of stars in galaxies. You have a diversity of galaxies, sort of large galaxies like Andromeda and smaller galaxies like dwarf galaxies, but all stars, they all contain stars, and stars are also sort of come in a diversity of shapes and colors and sizes. Not so much shapes, ignore what I just said. Different masses, sizes, and colors. So larger, more massive stars can burn at hotter temperatures, and these appear in bluer colors, and our smaller stars, like our own sun, have less mass, and they burn less hotly, and they appear to be redder. So if we look at a population of stars, the colors can be very useful in telling us about the age of that population in a galaxy, because these massive, bright, hot blue stars burn through their fuel much more quickly. So if we look at a population of stars and it appears more blue, that means that this area of stars is fairly young, because these blue stars have not yet died off. So as you can see in Andromeda, near the center, things appear slightly less blue. So in these regions, there's no sort of active star formation going on. And out in the arms of the galaxy, you can see that things appear more blue, and that tells us that star formation is still ongoing here. So for the star formation to be ongoing, this tells us that Andromeda has to have new fuel for these stars to form from. And the fuel for a star formation is hydrogen gas. So hydrogen gas exists in galaxies in multiple forms. So the stars form from the densest, coolest clouds of gas, which will be molecular gas. So the hydrogen cools down enough that it can begin to form molecules as opposed to just atoms. And in these dense clouds, they begin to collapse, and that's when stars form. Once these stars form, they let out lots of radiation, which begins to heat up and ionize the gas clouds around them. And you can start to see bits of this in this image in these sort of purple dots within the arms of Andromeda, because you can see that in our optical image. And one final form of hydrogen gas in galaxies is our neutral hydrogen gas. So this is just atomic hydrogen. It's cold. It just exists in a thin disk that rotates, a thin disk in the galaxy, which is rotating around the center. So you can't see this in the image because neutral hydrogen gas emits radiation at 21 centimeters, which is only visible to radio telescopes. So this optical image doesn't show the neutral gas there. Our inset image here of NGC 6946, on the left we have an optical image, as we see of Andromeda, and on the right we have an image taken using a radio telescope array of the neutral hydrogen, using a 21 centimeter line. So these two images are actually on the same physical scales. So you can see that the neutral hydrogen gas extends to far greater radius than the stellar material that we see with optical telescopes. And this is going to be important later, so I'm going to come back to that, but just bear it in mind just now. I'm going to finish off my shopping list. We have the dust. It's not going to be too important for this talk, but it makes up a small amount of mass in the galaxy, but you can really see it strongly in Andromeda with these dark regions. And in our inset image here, when we see the Milky Way in the sky, as you can see in some dark skies in Scotland and other places around the world, you mostly notice sort of the dark regions. And because we exist in the disk of the Milky Way, we're sort of looking through the plane. So what we mostly see is dust getting in the way so that we can't actually see the center of the Milky Way. So dust causes problems for observations. The dust is made up of just sort of grains of sandy material, and it absorbs the bluer light, heats up, re-emits it in the red, and that's why we sort of don't really see much light coming from these regions, aside from maybe slightly redder hues towards the center. One more ingredient in a galaxy, which again isn't too important tonight, but at the center of a galaxy, most galaxies contain a supermassive black hole. It's been covered in the news quite a lot recently because a couple of years ago we took our first direct image of a black hole, as you can see in the inset here. Now these supermassive black holes, whilst not important to this talk, are very important to galaxies themselves. They have the power to potentially even stop star formation in a galaxy and lead to the galaxy beginning to sort of die off by ejecting all the gas from the galaxy and ceasing the star formation, removing all the fuel. So these are sort of all the items that exist, and we obviously, of course, have our star of the show tonight, our dark matter. So the dark matter I'm sure you've probably heard about from lots of different sort of pop culture references, etc. And we know that it doesn't interact in the way that normal matter does. So it doesn't interact with electromagnetic radiation, so it doesn't interact with light, it doesn't interact magnetically. The only way that dark matter interacts with the rest of the universe is through the gravitational force, through gravity. So because it doesn't interact with light, when we look at our image of Andromeda, we of course can't actually see the dark matter directly, we can't detect it directly. If it did interact with light, I imagine this would probably be our view of Andromeda, because the dark matter is everywhere throughout the galaxy. It exists in this this halo form, and it extends far beyond the galaxy itself. But luckily we can't see it, so we can still continue to look at our lovely images of Andromeda. So if we can't detect dark matter directly, what evidence do we actually have that it is there and it exists? So when we actually started measuring the velocities of stars and galaxies, we found that the velocities don't make sense based on the mass that's there. So if we measure the velocities of stars in the disk of Andromeda, we find that the galaxy is rotating. And if we measure the velocities here, we can work out the only force acting on these stars is the gravitational force. And that dictates that the speed that they can rotate around the galactic center is decided by the amount of mass that's inside them. So this equation here, which I promise is the only equation in my entire talk tonight, you'll be pleased to know. Our circular velocity is decided by the mass enclosed and the radius at which the object is rotating. So if we use this equation, we can add up all the mass inside the radius that the stars are moving at. So we add up the gas, the dust, and the stars, everything that we can detect and measure. So we can predict the velocity at which these stars will be allowed to rotate, allowed to move. And when we do this, there's not enough mass there to generate the gravitational force to keep these stars on their trajectory. So this is similar to if you were in a car going around a roundabout. In the case of a car, the force that's keeping you going on your circular path is your friction of your tires. In the case of these stars, they're going so fast that it would be like going around a roundabout on ice. So there's not enough force there to keep them going on this path. So if you were going around a roundabout with not enough friction to keep you going around a roundabout, you would no longer be going around the roundabout. You would be off in a field somewhere. So if we start measuring these velocities at lots of different radii, we can start to construct what's called a rotation curve for the galaxy. So if we measure it as we go further out from the center, we get a rotation curve, which describes the rotational velocity at each radius. And this is the shape that we find when we do this for most galaxies. And if we add up the mass within each radius, we can see what we predict based on the mass that we know is there, so the stars and the gas, etc. And this is what we would expect. So as you can see, as we go to further radii, things should be moving much more slowly than they are. So we get this sort of drop off as we go further out, whereas what we actually see is that things stay at a constant velocity at high radii. So this was what Vera Rubin did in the 1970s for lots of different galaxies using hydrogen observations. So she looked at she knew the theory very well. Everyone knew that stars were expected to follow this dropping off in the rotation curve, and she began to take observations of velocities, rotational velocities, at greater and greater radii. And she exclaimed at the time that no matter how far out they went, they couldn't find this dropping off. Things were just remaining constant. And that was sort of our first evidence that there needs to be some mass which is unaccounted for to keep these stars and gas and material on the trajectory that they're on and at the velocities that they're going. So when we actually add in a dark matter halo, we are able to reproduce the data. So in the bottom left here, we have a figure from Anne-Marie Weimans, my supervisor in St. Andrews, from a paper of hers from 2007. So in the red dots, she measured the rotational velocities of this galaxy The first few red dots, the first set of red dots on the left are from the stars, and the final 4 are from hydrogen gas. So what she then does is this line here, if you can see my cursor, tells us what the rotation curve would look like with just the stars, this one with just the gas. And adding those together, we're not able to reproduce the red dots. But by adding in a contribution from a dark matter halo, it makes up the difference, and that is how we're able to reproduce the rotation curve for this galaxy. And that way we can quantify the shape and size of the dark matter halo. So this sort of leads us to the conclusion that almost all galaxies are existing embedded in these really extended dark matter halos. So you can see in this illustration here that the luminous matter, the sort of stars, gas, the galaxies that we know and love from our images, really only exist in the very, very central regions of this really extended dark matter halo. And the dark matter halo itself only becomes really dominant at these sort of outer radii. And we think that these halos are very important for how galaxies actually form. So our current understanding is that the dark matter halos form first, and then cold hydrogen falls into the gravitational potential caused by these halos and begins to cool and condense in the center and form stars and form the galaxies that we see. And we see that without these halos first forming and making the potential deeper to begin with, the gas wouldn't condense, wouldn't fall in and condense fast enough to produce the galaxies that we see today in the sort of timescales that we're at now from the start of the universe. So sort of continuing to talk on these massive scales, the whole universe wouldn't look the same without dark matter. So if we start from the Big Bang, we can use a cosmological dark matter simulation to fast forward from the Big Bang to now and see how the dark matter is expected to move and evolve under its own gravity. So just after the Big Bang, the universe was pretty uniform, but there were some sort of small perturbations where some regions were slightly overdense and some regions were slightly underdense. And then as the universe expanded and gravity took hold, the sort of overdense regions became more overdense and the underdense regions became more underdense. And if we fast forward to now, the simulations show that this structure known as the cosmic web begins to form. So this is sort of filaments and knots of dark matter that exist on massive cosmological scales. Excuse me. And this is predicted just from the dark matter by itself, but in a very rudimentary test on the right here, I just took some of the galaxies from the Sloan Digital Sky Survey and made a plot of their positions on the sky just as we would see them. And I've sliced them based on how far away they are. So the green galaxies are closest, the orange galaxies are slightly further away, and the red galaxies are further still. And even just sort of this rudimentary plot, you can already start to see these sort of filamentary structures and the knots begin to form, showing that the galaxies trace this large cosmic structure of dark matter, as we'd expect. So the more sort of formal way to do this, we can use these simulations and our observations to really fine-tune our dark matter model. So on the right here, you see the cosmic microwave background. So this is the leftover radiation from the Big Bang, and this shows these really small density perturbations that I spoke about. So these slightly overdense and slightly underdense regions. And if we sort of use the statistics of how these appear, you start our simulation from those initial conditions and evolve them forward with dark matter the way that we believe it behaves. We can then predict how it would appear today and how that changes based on how the dark matter behaves. So we use our simulations to fine-tune our dark matter model, and we understand how the dark matter behaves on these massive scales really, really well. We can really accurately predict from the cosmic microwave background until now, we can really predict the observations that we see these days very, very accurately. So on these scales, we think that we have a good handle on dark matter and how it all works. But we don't actually know what it is. Even the way that I'm speaking, which assumes that dark matter is a form of matter, is not actually that certain at present. But for the purposes of this talk, I'm going to frame it that way, because if we got into different theories of dark matter and different ways that we can explain the phenomena that we see, I'd have a whole other talk, and I've only got a set amount of time. So currently, the current leading theory for the last couple of decades has been that these phenomena are explained by dark matter, which is a form of matter that does not interact, and it's specifically called dark matter. And we thought that this explained everything very well, and we predicted where the particle physicists would be able to find evidence of it, and they still haven't really found confirmation. So it's starting to look a bit dicey as to whether we want this to be our leading theory anymore. So it could be that dark matter behaves differently than we expect, but then the alternatives would mean that we would have to rewrite our theories of gravity and relativity, and I don't think Einstein would be very pleased about that. So for the moment, we're still sticking with it. But luckily for me, I don't need to worry about this, because even without knowing anything about what dark matter is, I can still measure its effects and behavior, thankfully. So we understand it very well on large scales, but there are still issues, especially when we look on look at how dark matter behaves within galaxies. So if we use our dark matter only simulations, we can predict what shape the dark matter halos should be in the galaxy, in other galaxies. And when we do this, we find what's called an NFW halo. It stands for Navarro, Frank, and White, the three people who came up with this profile, tested it and showed that it spat out by the simulations. And you can see that it rises steeply in the center of the galaxy. So this is the density of the dark matter against the radius of the galaxy. So in the center, it continues to rise steeply with a slope about 1. And this is called a cusp. But when we actually measure halos observationally, specifically sort of dwarf galaxies, so smaller galaxies, some sort of show a region that doesn't rise steeply in the center. They show a flat region known as a core with a constant density within the central radius. And this is obviously a problem, because if our simulations don't match our theories and our simulations don't match our observations, then we've got a problem, because that means either the observations are wrong, which at this stage we're pretty set on them being correct, or unfortunately the simulations were wrong. Now the simulations, these were dark matter only simulations. So the only things that can be wrong is our theory of gravity, our theory of dark matter, or our assumption that dark matter isn't really affected by normal baryonic matter. So simulations are great. They allow us to test lots of different exotic theories. They allow us to compare to observations to sort of check which ones are correct, and to understand processes more in depth than we would just through observation alone. But they're only as valuable as the observations that we test them against. So to sort of get at this problem and work out which part of this simulation, which part of the theory was wrong, we want to measure halos for more galaxies more accurately, because that allows us more robust tests for the simulations, and should allow us to sort of work out exactly where it is that we're wrong. So how do we actually measure something that we can't see? How do we work out how heavy it is? How do we measure where it is? How do we go about measuring something that's invisible? So the answer to this is dynamical modeling, and that is what I do. It is what my supervisor Anne-Marie does, and it's a really neat way to sort of measure the dark matter halo. So I'm going to run through quickly how it works. I'm going to avoid any maths. There's an option for maths, but you'll have to ask for it, because I put it in as a bonus slide if anyone really wants to know it at the end. So dynamical modeling works on the premise that the motions that we observe are directly a product of just the luminous potential, so the potential caused by the stars and the gas, and the dark potential, so the potential caused by the dark matter. So in theory, if we could perfectly describe the potential from the luminous matter and perfectly describe the potential from the dark matter, we should be able to perfectly reproduce the motions that we observe. Now, in reality, These potentials are quite complex, so we do what is done a lot in astronomy. We simplify it and use an approximation. So the luminous potential we approximate by using the surface brightness. We make it nice and smooth, and it tells us where the luminous matter is. And then we use our understanding of stellar populations, so how stars work, stellar evolution, to convert this to a mass from the brightness. And this tells us roughly what the luminous potential looks like. So our observed motions we can get from integral field spectroscopy. Again, I'm not going to go in depth about how this works, but if you're really interested, please do ask me at the end, because I do have an extra bonus slide for that one as well. So it measures spectra at each pixel across the face of the galaxy, the area of the galaxy, and you can work out the velocities of the materials at different areas, and that gives us kinematic maps, so 2D maps of how everything's moving, which is one step up from the rotation curves that we saw before. So if we use a model, we can predict what these observed motions would look like if only the stars and the gas were present. And when we do this, obviously they don't match up, there's a discrepancy. So the modeling process then involves selecting thousands of different sizes and shapes of dark matter halos, and sticking them into my model, and then comparing what we predict with what we observe until we find statistically the best shape and size of dark matter halo that fits the observations. So the modeling process itself is what I'm going to skip for the moment because it is filled with maths and isn't actually that important for the talk. But the exact modeling process that I am working on using is a genes modeling, or the JAM process, the JAM method. So it's not the most sophisticated method. There are more sophisticated methods, but they require much more expensive data, which I'll come on to soon. But the aim of what I'm doing is trying to find sort of a cheap and quick and dirty way to find out, to measure some quantities about the dark matter halo, so that we can do it for lots and lots of galaxies. So you can map the entire dark matter halo, but that's expensive and requires lots of time and requires more sophisticated modeling methods. So what I'm looking to do is sort of measure it slightly less accurately, but for thousands of galaxies. So statistically significant sample of galaxies, so that we can compare our simulations to them. So as much as this is the quick and dirty, cheap way of doing it, it still takes 16 hours to measure a dark matter halo on my poor little laptop, which is working a lot harder than it was ever intended to work. So 16 hours should go down a bit if I use slightly more computing power, but it's not exactly just a back of the envelope sum that we're doing for this quick and dirty method. So now that I've spoken a bit about how dynamical modeling in general works, I'm going to move on to discuss a little bit about specifically what I'm doing. So this method sort of quickly measure it for lots of galaxies. So I'm going to introduce a galaxy. It's named 1000112704. It's a very catchy name. You can look at the galaxies from this sample in Marvin, which is SDSS's useful online web tool. So if you do want to sort of explore the sample and look at all the data available, that's where you can do it. And it's nicely presented for people to use without needing to download the data, etc. So here's our galaxy. On the left, we can see a nice image from SDSS. And you can see that it's a disk galaxy. It's fairly edge-on, so it's like a dinner plate. We're sort of looking at it that way. And this pink hexagon shows the area that MANGA, so that's SDSS's integral field spectrograph, can cover. So MANGA has this bundle of optical fibers. It points them at the galaxy, covering this hexagonal area, and it gets a spectrum for each individual optical fiber. And what we then do is the spectrum can be used to work out the velocities at each pixel, and lots of other quantities. Again, asking more about that later if you want to find out what else we can measure. But here, our first plot to the right of that is our velocities, stellar velocities. So the right-hand side of the galaxy is moving towards us and the left-hand side is moving away. And the nice sort of left-hand, right-hand split here tells us that this galaxy is rotating quite regularly. So there's no other galaxies flying by causing it to get disrupted. It's just rotating quite nicely and regularly by itself, which is good news for me because that means that the modeling method is going to work for this one. To the right, we have our velocity dispersion, and that's just a measure of how much the material within each pixel is spread out from the mean value that we see on the left. So if there's some material in the pixel that's going way faster than the velocity on the left, that will tell us. And if there's some material that's going way slower than the material in the other plot, then it'll tell me here. So these are just, they're what referred to as the kinematic moments. So the 0th kinematic moment is just the surface brightness, so the positions of where everything is. The first kinematic moment is the velocity themselves, and the second kinematic moment is velocity dispersion. It goes way more than that, but they're not important for tonight, and they're much harder to explain. So I'm going to leave those ones alone. But we've got the first and second kinematic moments. Now, our JAM method does make a lot of simplifications, and it also wants just one kinematic map to work from. So I'm going to combine these two. I didn't even put an equation on, but I square both the maps, add them together, and take the square root of what we've added until we get a VRMS map, or a VZZ moment for its Sunday name. So this has also been symmetrized and regularized because the JAM modeling method assumes that our galaxy is symmetric, which isn't quite true, but it's not too bad an approximation for a disk galaxy like this. So if I then give this input to JAM, it's going to find the best dark matter halo and the best inclination and the best a few other parameters that will reproduce these observations. And this is what our prediction looks like. So it looks like it matches pretty well. Statistically, it's a very good model for the data that we have. But if I then look at the rotation curve, it looks like this, which, if you remember from the start, is what things look like without a dark matter halo. So this is simply because the model doesn't have enough data. So it does match the data very well, but as you can see here in these blue and orange lines, the data is only in the very center of the galaxy. So the galaxy itself, this is just coming from the stellar velocities. So the stars only exist in the very center, and the hexagon is the region that MaNGA can have data from. So we only have data from the very center of our galaxy that we're trying to model. So if our model only knows about these central regions, it can do whatever it wants out here, and it makes no difference. So in the center of the galaxy, the dark matter doesn't actually have that big an effect. It's mostly dominated by the stars and the gas. So it's not any sort of dark matter halo could reproduce the central area, but be very different in the regions where the dark matter is most dominant. So this is the problem that we're trying to tackle. So what we actually need is some data from further out in the galaxy, further beyond the stars. So we're going to cast our minds back. Seems like a long time now to the start of the talk, when I mentioned the hydrogen that's present in the galaxy. So our cold neutral hydrogen exists in a thin rotating disk, which extends to far greater radii than the stars manage to extend to. But to get nice 2D kinematic maps like we have for the stars, for hydrogen, it's very observationally expensive. So it requires whole arrays of radio dishes to map it. So you need a whole arrangement of multiple dishes to get these nice 2D maps. So our expensive radio astronomy can get us these lovely 2D maps and can get us wonderful dynamic models that will map the entire halo. But we only have array observations of galaxies for just a handful of galaxies. And for reference, every time someone models the dark matter halo of one galaxy using this, that's one whole paper that gets published. So what I'm wanting to do is use cheap radio astronomy data. So just one single dish. And this is what it looks like when you point one single dish at a galaxy. It is much less information than you get when you use the whole array. So this is just a spectrum that tells us how much radio flux, so how much signal is being taken in by the dish against the frequency. So this is centered around the 21 centimeter wavelength, because that's where hydrogen emits. And the reason it's got this nice wide double-horned profile is because the gas in the galaxy is rotating. So as we saw with the image above, one side is moving towards us and one side is moving away, which means on one side the signal is redshifted away from 21 centimeters, and on the other side the signal is blue shifted away from 21 centimeters. So the width of this doubled horn profile actually tells us the rotation speed of the gas. So as much as I can't sort of straight away tell you how fast this galaxy is rotating just from this profile, I can measure the width and then work out the rotation speed of the gas. And what that should do is give one extra data point at these large radii that we should be able to tell the model that it needs to do a better job of fitting things out there, because we're going to tell it what it needs to look like. So thankfully, this is an actual observation of the galaxy that we met before from the Green Bank telescope in the United States. And this is thanks to Karen Masters and Dave Stark, who are running a MANGA follow-up project. So they're taking single dish observations like this one for as many of the galaxies in the MANGA sample that we saw before as they can sort of manage to do. So if I take our measured velocity from this for that galaxy and add it back onto the plot to see how well the model that we generated before fits these outer regions. And you can see that it's not fitting in the outer regions because we didn't tell the model about anything out here. So ideally, what we're going to do is tell the model about the velocity out in these regions, and what it should do is select a better dark matter halo that's going to be able to reproduce the data out here and in the inner regions. And from that, we'll be able to measure quantities about the dark matter halo that can be predicted by simulations. So the next plot I'm going to show you is a work in progress, because telling the model about the hydrogen is what I'm still working on and probably what I'm going to spend my Christmas doing, because this model doesn't really want to be told about the hydrogen. But that's what I'm doing. So what I've done is just checked that actually halos can exist that are going to reproduce the data in the center and the outskirts. So this is me just manually adding some hand-picked dark matter halos to sort of see what kind of range of halos can exist. So between the gray and the red lines, the gray and the red lines both fit the inner data fairly well, but they also leave space that the outer regions can be fitted to fit our hydrogen point. And none of these models know about the H1 yet. So ideally, here's an artist's impression of what will hopefully come out from our modeling software once I tell it about this little red dot here. So what this allows us to do is measure sort of the fraction of dark matter existing in the galaxy for lots of galaxies. And we'll be able to test our simulations against that, because in the simulations you can very easily measure the fraction of dark matter in the galaxies. So simulations allow us to sort of predict from our theories what the observations would look like, so what the dark matter fraction would be for all sorts of sizes of galaxies, all sorts of types of galaxies. And what I'm doing is measuring the dark matter fraction for all sorts of sizes of galaxies and all sorts of types of galaxies. Because our observations and our simulations have to be able to describe the diversity of sort of the galaxy population. So if our dark matter halos look one way in one type of galaxy, our simulations have to also show our dark matter halos looking one way in one galaxy. So our simulations allow us to test different types of dark matter. Running from the start to the end, we can see what fraction of dark matter would be present in galaxies if it was warm dark matter, or fuzzy dark matter, or self-interacting dark matter, and all sorts of other weirdly named types of dark matter that people have come up with and theorized about. And they can also do it for different theories of gravity. So if we did have to throw away Einstein's relativity, people are already making simulations that try out different kinds of gravity to see what we would expect to observe. So the most accurate measurements of dark matter halos, where we sort of can map the entire halo, do use this expensive array data, but that can only be done for a handful of galaxies, as I mentioned, and this should allow us to take some measurements for a large sample of galaxies. So that should give us more of an idea, a more diverse sample, which will allow us to sort of give one extra way to constrain our simulations and check if they match the observations. So looking further to the future, I'm part of the WEAV Aperitif survey. So this is a survey which is a collaboration between a radio array in the Netherlands and an IFS, an integral field spectrograph in Tenerife. So the running theme of this talk has been how radio arrays and integral field spectrographs can work together to give us really good models. So as you can imagine, this is what we're hoping to do with WEAV Aperitif. So in the Netherlands, Aperitif is using the WSRT to collect this expensive resolved two-dimensional H1 data that we would like for our really sophisticated modeling methods. And the William Herschel telescope on Tenerife has a new IFU just been attached to it. That's a lie, it's not attached to it yet. It got shipped to Tenerife, but it's not been put on the telescope yet because I've had a few delays. But it's going to be attached to the telescope soon, touch wood. And it's going to collect the stellar kinematics similar to MANGA, but MANGA uses a 2.5 meter telescope. The William Herschel telescope is 4 meters. So we're going to get stellar kinematics, which are even better than MANGA. And we're going to have the expensive resolved hydrogen data from Aperitif. So the combination of the two should allow us to use this more sophisticated modeling method, Schwarzschild modeling, which will allow us to map sort of the whole dark matter halos for this sample of galaxies. Now they're hoping to do it for 500 galaxies. Of that sample, I imagine maybe half or just under half will be able to be modeled properly. I've not actually started looking at the data properly yet because they've not taken it. So it remains to be seen, but we're hopeful that we should get upward of 100 or 200 galaxies that we're going to be able to properly map the dark matter halos of, which is really exciting going forward. And it also means I'm going to have prettier pictures than those little black spectra that we just get from the single dish data. So in summary, we don't know quite what dark matter is yet, but we do know that it's there and we are able to measure it. It is what I do every day sitting in my bedroom. And we do this using dynamical modeling, which compares what we expect to see in the motions of the galaxies to what we actually observe in the motions of the galaxies. So by using MANGA and the single dish data, I'm going to hopefully get sort of easy peasy measurements of just the fraction of dark matter in lots of galaxies. And then moving forward, hopefully, if coronavirus and Brexit allow us, I'm going to get data from the WEAV Aperitif survey. And that will give us this expensive H1 data that we need to do this really sophisticated modeling method. So the future is looking bright for dark matter because hopefully this is going to give us accurate measurements in lots of galaxies for us to test our simulations against. And hopefully we'll pin down what dark matter is, how it behaves, and what it's doing in our galaxies. So with that, thank you for listening. Hopefully this was interesting. Thank you to David and June for setting this up and doing all the technical side of things. So yeah, thanks. If you have any questions, there are some bonus slides. So if you remembered which topics had bonus slides and you pick one, you get to see more of my wonderful graphic design. And with that, I will hand back to June and David.
Thank you ever so much, Stephanie. That was really superb and particularly good because of the complexity of what you're trying to convey in your talk with some clarity there. I don't know if David's got pictures, questions coming in yet, or if we can hear them.
We'll try and see if you can hear me.
Excellent. Yep, excellent.
I don't know, my mic's gone a bit flaky. Last week it was this. Last time it was the speaker, this time it's the mic. But yeah, we've got, definitely everybody's really interested in the bonus slides. So I think, yeah, if you've got anything on the maths, and I'm particularly interested in the integral field spectroscopy, because that sounds like something that would definitely be of interest to us. So yeah, any of the bonus slides, but the maths stuff and the integral field spectroscopy would be of interest.
Definitely. I knew if I dangled bonus slides in front of people, they'd jump at the chance. So I specifically missed out maths in case people didn't want it, but you asked for it. So this is how our JAM method works. It was developed by Michele Capillari a few years ago now. And our first step is that we use what's called a multi-Gaussian expansion in our surface brightness approximation. So that means that we take our really complicated image of how the stars are distributed in the galaxy, and we just smooth it all out and we describe it as a stack of Gaussians on top of each other. Gaussians are just a mathematical shape of a profile. And this is helpful because the Gaussians are really simple and it allows our equations to work quickly and efficiently and be solvable, which is always good. And our dark matter potential is just added on top in the same way. So I can make a MGE, a multi-Gaussian expansion of the surface brightness of the galaxy, and I can also make an MGE of lots of different types of dark matter halos. So adding those up, we can sort of see where the mass in the galaxy is. So JAM then works using Jean's equations. Now these come from what's called the collisionless Boltzmann equation, which is from, I've suddenly forgotten the name of the entire field, thermodynamics. It's been a long time since I did undergrad. Yeah, so the collisionless Boltzmann equation comes from thermodynamics, and it describes the 6-dimensional phase space distribution of stars in a gravitational potential. So all that means is it tells us the positions and velocities. So it's 6-dimensional because we've got X, Y, Z positions and X, Y, Z velocities for all the stars in a gravitational potential of our choosing. So here are the equations. So if we look here, our phi is our gravitational potential. N tells us our number density. The V's and the X's are our positions and velocities, the other way around because I said them the wrong way. The V's are the velocities, the X's are the positions. And T just tells us that this equation is going to tell us how it varies in time. So these equations are not generally solvable unless we make assumptions, which is why when I looked at our kinematic map for the galaxy that I introduced, it had to be symmetrical. And it had to sort of be smooth. But when we make these assumptions, they become solvable. And that's what, under the hood, that's what the code's doing. It's solving these equations for different potentials that are described by these Gaussians. So it's not too much maths, unless we go really in depth. But that's a quick taster of what the code actually does. If we want information on integral field spectroscopy. Here we have information from MANGA. So that's SDSS's integral field survey, integral field spectrograph survey, which very excitingly, despite all the coronavirus delays and other delays, it ran for 10 years, and last month it finished and hit its 10,000 galaxy target. It has observed 10,010 unique galaxies, which is very close to the target, but we did just get over it. MANGA uses the telescope at Apache Point Observatory in America, and they have these big plates. I should have included a picture of one. These big metal plates with individually drilled holes for the galaxies on each region of the sky, and through them they stick their little hexagonal bundles of optical fibers, and they take full optical spectra for each fiber across the whole galaxy. So here is a spectra. This is from 10001-12704, because may as well stick with it. And what we see here is this is the spectra coming from the galaxy, and these are the emission lines that we know come from stars, and they're all mapped on there. And to work out the velocities from across the galaxy, we look at where we would expect these emission lines to be, and then where they actually are, and that just tells us how much they're redshifted or blue shifted, and that tells us the velocity at which they're moving. So looking at the different wavelengths that they appear at, we can work out how fast that region of the galaxy is moving compared to us, and also compared to the galaxy as a bulk, if it's moving towards or away from us. So they can measure the velocities, but they can also find the flux from independent lines. I made these really small for some reason, I can't remember why. But on the left, we can see the emission coming from H alpha. So each pixel whiter tells us there's more, and this tells us how much H alpha is from ionized hydrogen. So this tells us which parts have bright young new stars that are causing the hydrogen to become ionized and glow. The next one, this one tells us where all the oxygen is. So oxygen, ionized oxygen specifically. So oxygen is only going to become ionized in really, really hot regions. So it tells us the center of the galaxy, there's lots of ionized oxygen, as you would expect. And then this traces quite nicely the spiral arms, because that's where all the hot blue young stars are. And over to the right is a quantity called D4000, which tells us how much, again, how many young blue stars there are in each sort of region of the galaxy. A lower number means more young blue stars. And as you can see, these darker regions line up in this band with where we see the ionized gas from the young stars, the ionized oxygen from the young stars, and we also see that the D4000 lines up with those two. So MANGA has been really useful over the last many years and for many years to come in terms of looking at chemical properties across the galaxies, sort of how star formation works, velocities, dynamics, etc., etc.
Yeah, that's really interesting. It's certainly some interesting techniques for teasing the data out of what's available. We've got a couple of other questions and lots of appreciative comments about people enjoying the talk. Phil's asking, will the square kilometre array be contributing to any of this research?
Not mine specifically, that I've planned at least, possibly in future. I can't remember whether the square kilometre array, it'll allow better spatial resolution. So it could actually be very helpful in working, sort of pinning down more focus on sort of which regions are moving at which velocities. But I don't have any plans within my PhD at least, so within the next few years to use it. But when it comes online, who knows what I'll be doing.
Yeah, possibly you'll still be doing the same kind of research, so it may come into that. I've also a question about what kind of tools you use for the software for your simulation. So everything that I do runs in Python.
I'm running Python 3.7, I think, and the JAM code, the genes modeling code, Michele Capillari, I think, has it publicly available, and it just is just installed into Python as a module.
Right. I think that's all the questions from there. Oh, hang on. Got another. Oh no, sorry, nothing. That's not a question. Yeah, I think that's all the questions for the moment. So yeah, thank you very much, Stephanie. That's
Not
really
a problem.
fascinating stuff. June, you want any?
Yeah, no, just to say thank you very, very much. I mean, just an excellent talk all round. And clearly everybody at the Dundee Society would like to wish you well with the remainder of your PhD, and of course the next bit where perhaps you could come back someday and tell us where this takes you after your thesis is finished. But that was wonderfully presented. Thank you very much indeed, Stephanie.
Thank you, and thank you very much for having me. It's been wonderful.
Our pleasure, our pleasure.
Right, just a couple of things before we switch off the stream. Graham's asked me to remind you about membership fees and calendar requests. If you're wanting calendars, let Graham or Tony know, and pay your membership fees and calendars payments to Graham, please. A couple of other things which, as you know, my big interest is in spaceflight. Chang'e 5, the Chinese lunar probe, will be doing its lunar orbit insertion tomorrow. I don't have an exact time for that, but it should be landing, hopefully, fingers crossed, on the moon at 8:30 UTC on Sunday, and then lifting back off, hopefully, with a lot of samples on board on Wednesday. So that will be something worth keeping an eye on. We've also got SpaceX on Monday. Hopefully will be doing their 15-kilometer hop with their Starship, which is the new, very large spacecraft that they've been developing, hopefully for lunar and Martian voyages. So that's the first 15-kilometer full test flight with the awesome Raptor engines. We've got a couple of other things. Jim's asked me to remind you also of newsletter submissions. Please get those in. And Phil's asked if Stephanie can maybe mention what the Schwarzschild model, which will be used for the 500 Galaxies, is about. If you can maybe briefly give us an explanation.
So the Schwarzschild model removes the requirement of it being all symmetrical, and it works by mathematically it works out all of the allowed orbits of stars, and then it's an orbit superposition method. So it superimposes all those orbits on top of each other, all of the statistically allowed ones, based on the potential. And when you add them up, you can see you give them different weighting so that it reproduces the surface brightness based on how many stars are in each type of orbit. And then you can, based on that weighting, predict the predicted kinematics, so the motions, and compare that to the observations. And then that allows you to do the same thing and add in a dark matter halo and find the right one, etc., etc. So it's more sophisticated, it takes longer to run, but it removes some of the simplifications that we need to do the genes modeling and should allow us to get more in-depth measurements.
Right, so yeah, that sounds good. Yeah, you just need more bigger computers. And
yeah, not this poor little laptop, I don't think.
Yeah, get yourself a large computer and some graphics cards in it to get the GPUs running on it.
Yeah.
Right. A recommendation for your laptop, though.
Yeah.
It's doing a very good job, this little laptop.
Yeah. That's all the questions we have at the moment. But as I said, lots of appreciative comments, and everybody's really enjoyed that. So thank you very much.
Okay.
Anything else you want to add, June?
No, really, just to absolutely. Thank you. That was lovely, and very much hope to be able to hear where this goes in the future, because this start sounds pretty exciting work. So it would be great to see where the next part comes. Yeah.
Yeah, fingers crossed.
Oh, I don't know. I think looking pretty good without luck. I think you're doing grand.
Right.
Thanks again.